Okay, let's start our lecture. Today we will discuss some properties of a Brownian motion. Let me recall you that a week ago we formulated a Donsker theorem that stated that if you have a sequence of independent, identically distributed random variables, zero mean and with finite variance, then the scaling of a random walk, we scale time n times and space square root of n times converges in distribution to a Brownian motion as n tends to infinity in the space C0 infinity. And let me recall a few facts that what is the metric, and let me recall that as psi n is a sum psi1 plus psi2 plus psi n, and for natural n, s of 0 is 0 by definition. And so the random walk is defined only for non-negative integers, but then we always extend Sn to all non-negative numbers by linearity. So this is our agreement. And we consider a space C0T with supremum norm. So this is Banach space with supremum norm F 0T is maximum of F of T in 0T. And this is complete separable metric space, and the space C0 infinity is a metric space with a distance. I'll write here like rho or rho infinity, f and g. So these are functions, is integral from 0 to infinity f of s minus f minus g supremum norm in 0t minimum 1 times e to the power minus t dt. And the problem was to prove that this is really a metric space, complete as a separable, and convergence in this space, so Fn converges to F here with this metric, is equivalent to uniform convergence on the compacts. So for every t, Fn converges uniformly on 0t, or in this space to use a function f. This is integral is convergent because I write here distance minimum 1. So here I may take distance minimum 1, or sometimes people take arctangents or f minus g norm in 0t divided by 1 plus f minus g. 0t instead of this. So all these metrics are equivalent, and convergence is equivalent to locally uniform convergence. There was also one problem about stochastic processes with continuous trajectories and random elements with values in the space of continuous functions. And let me formulate the result. And the result is x of t is a process, is a stochastic process with continuous trajectories if and only if the mapping omega to, so x considered as a function of t as a mapping from omega to x dot omega. So this is continuous function in C0t is measurable. This means that x is a random element as a function of omega is a random element. X is a random element with values in C0t. With values in metric space C0t with Borel sigma algebra. The proof. So there are a lot of proofs. One is to show that cylindric sigma algebra in C0t coincides with the Borel sigma algebra. I will do it. So I will present you another proof. Okay, at first, this direction. Assume that X is a random element with values in C0t. I need to show that for every t, x of t is a random variable. So we have to show that x of t is a random variable for every t in 0t capital. Okay. Observe that x of t is a function of x. Let me denote this function p, where pi sub t is a function from C0t to R, defined by pt of f. So f is the function, continued function, is a value f of t. It's easy to see that pi sub t is continuous. So its Borel function pi t is measurable. So pi t of x, which is equal to x of t, is a measurable mapping from omega to r, is a random variable. So we prove that x of t is a stochastic process. Now, another direction. So we know that for every fixed t, x of t is a random variable, and for every omega, x as a function of t is continuous. Is continuous function of. Now let us consider the following process, x of t. So linear, so this is x of t, and xn, we do the following trick. So let this be uniform partition of the interval 0 t. So this distance is t over n. And we consider this linear approximation. Formally, x of t is equal to sum k from 0 to n minus 1. Indicator t in so the case point is tk is kt over n. tk plus 1. And now x of tk. So I just need to write equation of the line. Plus t minus tk x and the increment x of tk plus 1 minus x of tk. Okay, and so if t is tk, then value is tk. If t is tk plus 1, then value x divided by tk plus 1 minus tk. When the value is tk plus 1. Oh, okay, and for the last interval, I have to include tk capital. So this is random variable because x of tk is random variable, x of tk plus 1 is random variable. These are, okay, this is just numbers. The next step, it can be seen that this function is a measurable function from Rn plus 1 to C0t. Okay, and coordinates are this as a measurable function of these coordinates. So I leave this question for you, but why it is measurable? Because it's continuous, for example, in these variables. And we consider uniform metric here. So xn of t are really random elements with values in C0t. So xn is a random element with values in C0t. And now for all omega, xn uniformly converges to X. Because X has a continuous path. So this is mathematical analysis. So X n converges to X in a metric of C0T. And we know from the course of measure theory that the limit of measurable functions is measurable. So X is measurable in omega, and we consider X as a function with values in this metric space, and theorem is proved. Questions?
So we consider xn like a function from firstly like a function from tk, and then tk xtk.
No. Yes. So, let me write here. Yes, so let's define the function fn of x1, x0, x1, xn s. Sum of these indicators, tk plus 1, tk plus 1, xk plus t minus tk times increment of x divided by increment of t. And this function is a function from Rn plus 1 to the space of continuous functions.
Okay, and then we put there
And yes, and
variables, and
then we plug here random variables, x of tk, and here x of tk plus 1 minus x of tk. Then fn of this random variable is random element with values here. And it can be easily seen that this function is continuous, so it's measurable.
Yes, I understood. Thank you very much.
And in the end of the proof, we not only get that x is measurable, but we also get that x is continuous as a uniform limit of continuous
No, we know that we know from the very beginning that for every omega, this function is continuous in t. And we know from the very beginning that for every t, this function is measurable in omega. But we do not know, is this a measurable function from omega to the space of continuous functions?
Okay, I see. Thank you.
Use the fact that x is continuous to build such approximation.
Yes, that's true. And my next aim is to find the distribution of the maximum of, problem. Find distribution of maximum of a Brownian motion. Before we start solving this problem, we have to discuss the following question. Is it a random variable? The answer is yes. And just few well-known exercises from measure theory. And exercise is this. So let xn be a sequence of random variables. Prove that supremum of xn infimum of xn lim sup lim inf are random variables, okay, with values in R with values in compactified line. So supremum and infimum may take values plus and minus infinity, and prove, for example, that the set of omega such that, for example, the limit exists and finite or infinite is measurable set. By the way, question, how to prove this? For example, for supremum. Any ideas?
We for sure know that it's measurable that xi, any xi bigger or less than bigger than something, and we need to cleverly make a condition that supremum of xn is bigger than something if and only if is something.
Yes. Exactly. So, for example, for supremum, it's sufficient to prove that for every C in R, this is a measurable set, subset of omega. And this can be written as intersection that every psi n is less than C. So if this is true, then all psi are less than or equal to C, and if all psi are less than or equal to C, then supremum is less than or equal to C. And this is measurable, and we have countable intersection. So countable intersection is also measurable. Okay, another exercise. Maximum of a Brownian motion is a random variable. How to prove this? Ideas?
We use the fact with supremum and a continuity of V of t.
But here you see uncountable set.
Yes, but because bt is continuous, we can use rational numbers, for example.
Yes, that's true. So maximum of B of t is equal to supremum, where we take supremum over the countable then set, for example, rational numbers of B of t. So we know that this is random variable, so this is random variable. Great. And now the result. The distribution of maximum of B of t is equal to the distribution of the absolute value of the normal variable, zero mean, variance t, for every t greater than 0. Proof. I will consider the case t is 1, you may, so the exercise is extend my proof for arbitrary t, and you may just follow my rule or use self-similarity property of a Brownian motion. And okay, so this is remarkable exercise. It's known that for every c greater than 0, the distribution of b of ct is equal to the distribution of square root of t b of t. Okay, the proof for t is 1. Recall Donsker theorem that scaling limits of random walk of random walks is a Brownian motion. And let's consider specific random walk. So let xi k be symmetric random variables that take values 1 and -1 with probability 1/2. Xi k are ID copies of this random variable. Expectation of xi is 0. Variance of xi is 1. One moment, I don't remember. So here I forgot to write sigma in the denominator. I'm sorry. Okay, and I know that as xi of nt over square root of n converges in distribution to the distribution of b of t in 0, 1 in a metric space C 0, 1. The second step, maximum, let's define f of okay, of f as maximum t in 0, 1 f of t. So f is a function from the space of continuous functions to R. And f is continuous, so it's well known that for every f and g continuous functions, maximum of f of t minus maximum of g of t does not exceed maximum of their difference. And this is just distance between functions f and g in this metric space. So function f is continuous. Hence, by continuous mapping theorem, f of ask psi of nt over square root of n dot over square root of n, a random variable, a random element with values here, converges I'm sorry, this is implication. So let me read. So converges in distribution to f of a Brownian motion. So the problem is to find so maximum t over 0, 1 as psi n t over square root of n. So this sequence of random variables converges in distribution to maximum of bt t in 0, 1. And so we have a random walk that starts from 0. Every instant of time, it jumps one step up or down. Well, at first I can write like maximum. So let me denote nt by s. Then s belongs to 0 n. S psi of s divided by square root of n. And I wish to say that maximum may be attained only at integer number. So at some integer number. So this maximum is equal to maximum of s psi of k over square root of n, where k is between 0 and n integer number. And we know how to calculate the distribution of this number. So we know that the probability that maximum k between 0 and n as psi of k greater than or equal to some integer number, say L, is equal to probability that s psi of n greater than or equal to L plus probability that s psi of n greater than or equal to L plus 1. L is integer number. Now let's consider, for example, distribution function of this, or let's calculate probability that maximum of s psi of nt over square root of n greater than or equal to some non-negative number x. X greater than is real number. Well, so make these transformations. This probability is equal to probability that maximum over k between 0 and a s psi of k over square root of n greater than or equal to x, or we can move square root of n to the right hand side and obtain here this. X square root of n may be not integer number, and we know this formula only for integers. But look, if x over square root of n is not integer, then the fact that maximum is greater than or equal to x square root of n means that maximum is greater than or equal to integer part of this plus 1. So we may consider two cases. This number is integer or this number is not integer. Well, for simplicity, assume that this number is integer. Oh, okay, not integer, and let me round it up to consider not integer part, but round to above. Okay, we have this probability, then apply this formula is equal to probability that maximum, oh no, without maximum, just ask psi of n greater than or equal to this number plus probability that ask psi of n is greater than x square root of n plus 1. And now recall the central limit theorem. We know that ask psi n over square root of n converges in distribution to the standard normal variable. So let me divide left-hand side and right-hand side by square root of n. And well, I formulated the following result, that if psi n, okay, the following conditions are equivalent. Psi n converges to psi if and only if we know that distribution functions converge to the distribution function of psi for every x a point of continuity. Of f psi. But here we have different number. Okay, this number converge to x and this number converge to x, but can I apply this this property? I need the following. So if and only if f xn of I xn converge to f of x for every sequence xn such that limit xn is x, where x is a point of continuity. So I need more advanced result, but
excuse me, do we have to write f psi n of xn? So
yes, I need this. You see, well, this is not the distribution.
okay, so
well, and
the
okay.
point also changes.
Yes, I agree. We should write here greater and then add 1 here, and to write here and add 1 here, and well, to be honest mathematician, I have to write here greater, and then if you have this, then you have a result for the distribution functions. But let me explain that we have all tools to prove this result almost for free. Well, let me denote this by xn. Okay. Well, I need to prove this. And xin less than or equal to xn. Let me represent this as probability that xin plus x minus xn less than or equal to x. I know that xin converges in distribution to xi, and this converges to 0. And we know Slutsky lemma that if one sequence of random variables converges in distribution to xi, and another converges in probability or in distribution to a constant, then some converge in distribution to the sum. So this sequence converge in distribution to xi. So the limit of this is equal to probability that xi less than or equal to x for every x point of continuity of the distribution function.
I'm sorry. In our equation with probabilities, we had our psi, our thing greater or equal than something. Yes, but
yes,
we changed it greater, strictly greater, and added +1. I suppose.
Yes, because
I
you
suppose
see,
we should make the opposite. If greater, but mean -1.
thanks, -1. Yes, you're right. You're right. Yes, yes, yes. All of these random variables are integer values. Yes, -1. Totally. Yes, but you see, yeah. So here, greater or greater than or equal is not so important. So we use Slutsky lemma, and we know that. So from this observation, we have that the corresponding limit is equal to probability that n01 is greater than x plus probability that n01 is greater than x. So we have this. So we have proved that limit of maximum probability, maximum s psi nt over square root of n greater than or equal to x is equal to probability, to probabilities that n01 is greater than x, or we know that this distribution is symmetric. Probability that absolute value of n01 is greater than x. So limit of distribution functions is equal to the probability that this random variable is less than or equal to x. And this distribution, so we have this for every x positive, and we know that this is continuous random variable. Oh, yes, a random variable with continuous distribution. And the case when x is negative is trivial. So we have this equality for all x's, and the theorem is proved. Okay, questions? If not, then we continue. And the next problem is the following. Let x be a positive number. And I want to define the heating time of x by tau x. So tau x is the first instant when the Brownian motion hits S. So tau is a function of B. The first question is the following. Is tau x a random array? With values in 0, infinity. So if this set is empty, we say that tau x is infinity. The answer is yes, so this is exercise, but we will see this easily a little bit later. Okay, we may say that, okay, let me define the function g from the space C0 infinity to R as here. So g of f is infimum of t such that f of t is equal to x. And infinity if to R. Exercise is proof that this function is measurable. And measurable. And the second question, is G continuous? And let us discuss this question. So assume that Fn converges to F in C0, in C0 infinity. So does this imply that G of Fn, so the heating times, converge to G of F? The answer is no. This function is discontinuous. Let me show the example. Assume that the function f touch x, then it is equal to x, and then go here. And Fn are shifts of this function down. So this distance is 1 over n. So heating time G of f is equal to this point, and these green functions hit there, and the limit of these points is equal to this number. There are many other counterexamples. For example, you may touch a point and go down. And in this case, g of fn is equal to infinity, and g of f is finite.
Sorry, can you please explain what is f and what is fn?
Just continuous function. So f is red, and green is f minus 1 over n.
And we go upper to...
Yes, so green functions converge locally uniform, okay, even globally, uniformly to red function as n goes to infinity.
Yes.
But the heating time do not converge. The heating time of x, they don't converge. Moreover, for red function, heating time is equal to this number, but for green, they're infinite. So you don't have convergence at all. Well, we can't apply directly continuous mapping theorem because this function heating time are discontinuous functional. Well, there were extension of continuous mapping theorem, and it states that if, for example, psi n converges to psi, and if probability, and if g is a measurable function, and if probability that psi belongs to the set of discontinuity of g is 0, then g of psi n converges in distribution to g of psi. So we know this theorem. So one way to investigate heating time for a Brownian motion is to prove that probability that Brownian motion, that path of Brownian motion belongs to the set of discontinuity of this map is 0. So that for almost all paths of Brownian motion, this heating time is a continuous function. Yes, actually, this is true. And think about this and try to find a rich set of functions, f small, such that g is continuous at f. And now let me investigate this heating time, tau x, for a Brownian motion. And so I will not use Donsker theorem, so I may, but there is another way. There is some duality between tau x and a maximum of a Brownian motion. Let this point be t, and probability. Okay, let's compare events. Tau x. Assume that tau x is less than or equal to t. What can we say about path of a Brownian motion on this interval, 0t?
Its maximum
Yes, then maximum of a Brownian motion on the interval 0t is greater than or equal to x. Okay. I forgot to mention that assume that x is positive and tau x is less than or equal to t if and only if the maximum is greater than or equal to x. Well, b of s is continuous function that start from 0. So if maximum is greater than t, starts from 0, maximum is greater than or equal to t, then assume that maximum is attained somewhere. Then there is a point between 0 and the point of maximum where you really hit x. And other direction, if tau x is less than or equal to t, then there is a point where b of s is equal to x, so maximum is greater than or equal to x. So this probability, which is the distribution function of tau x at the point t, is equal to the probability that maximum of a Brownian motion is greater than or equal to x. And we know distribution of maximum of a Brownian motion. So n absolute value of n0t is greater than or equal to x. And if I wish to find density, I need to differentiate this probability with respect to t. Okay, and how to differentiate it? Please help me. Well, I know how to differentiate it with respect to x because I know how to differentiate distribution function, and this is 1 minus distribution function. But I need to differentiate in t. Well, let me use self-similarity property of a Gaussian random variable. Yes, then this probability is equal to probability that square root of t times absolute value of n01 is greater than or equal to x. Let me move square root of t to the right-hand side. Let me do like this. And I would like to write this like 1 minus probability that n01 less than x over square root of t. Well, I wish to have the distribution function, so let me write here less than or equal. So I know this distribution is continuous, and I wish to write this. So let me write this like 1 minus probability that n01 belongs to the set from 0 to x over square root of t. No,
No, then not from 0. I suppose we should just get rid of the modulus and get to.
Okay. Yes, you're right. It's easier to write at first here. To write 2 here. Yes, and to write that this probability is equal to 2, 1 minus probability that n01 is less than or equal to x over square root of t. This is correct. So 2, 1 minus distribution function of n01 at the point x over square root of t. And now we differentiate left-hand side and right-hand side in t. So the density of tau x at the point t is equal to derivative of this. So derivative of 1 is 0, so minus. Derivative of this is the density of the standard normal distribution that taken at this point, and times derivative of x over square root of t in t. So here we write n2. So here we write so t to the power negative 1/2. So minus 2 times negative minus 1/2 f n01 equal x over square root of t times x times t to the power minus 3 over 2. And finally, the answer is, so this cancels out. So 1 over square root of 2 pi e to the power minus v squared over 2, so x squared over 2t times x t minus 3 over 2 for positive t. So theorem, the density of tau x is equal to e u x times e minus x squared over 2t, where x is positive number. Questions?
Does this distribution have some name?
I don't know. Sorry, maybe it has some name, but really I don't know. But I have a question. Is it true that integral of this function over from 0 to infinity and integrate with respect to t, is it 1?
Well, we know that like we can compare it to the integral of so for normal distribution it looks very similar to.
We know the integral. The integral is this. If you integrate from 0 to t small, and if t goes to plus infinity, then this number converges to 0. So this function converges to 1/2. Well, this difference converges to 1/2. So this expression converges to 1. So this is really a density of tau x. And tau x has, so it is a random variable, real valued. So it doesn't, so it takes value plus infinity with probability 0. So this is, so Brownian motion really hit with probability 1 every positive point, and the hitting the distribution of heating time has this density, or for negative axis we may use similar arguments, or we know that Brownian motion is the same distribution as minus Brownian motion, and this process hits x if and only if this process hits minus x. So for all real number x's, the distribution of heating time is equal to absolute value of x times this exponent divided by the square root of x. Okay, that's all for today. Thank you for your attention.
Thank you very much for the lecture.
Thank you.